Okay, welcome to lecture or lab, actually. So, welcome to lab. We'll get started here in just a sec. Give everybody a second or two to come in. Uh, like I said before, at the end of lecture, I think we're going to continue actually lecturing here in lab. So, we're going to continue on where we were talking about earlier today, just to kind of keep on pace. And again, the lab that was scheduled for today does cover some of the information that we haven't got to yet. So this way we could get to it, and then you'll be able to do the lab okay. Done with it. So again, we're not going to actually do the lab today. We're going to move it to Monday. So on Monday, we will do experiment number 3. Because I think on Monday there was just some lecture scheduled anyways. So that should be okay, I think. So no experiment is going to be due today. And again, we'll pick up with experiment number 3 on Monday. So what we're going to do again during this time is we're just going to kind of finish up hopefully this chapter and get through all the stuff that we need to kind of get through. And we'll just kind of move the lab to Monday. And like I said, there was no official lab schedule for Monday. So it'll be okay. It's just going to be some lecturing, I think. So we'll just do the lecturing today instead of Monday and stuff like that. Any questions on that? And again, chat box is there. So go ahead, put that you're here. And then also, obviously, you can use it for any questions that you have as we go through these, the rest of this chapter. So again, for those people just coming in, we're not going to actually do experiment number 3 today. We're going to move that to Monday of next week. We'll do experiment number 3. So we're going to continue on lecturing with what we've been talking about. All right, so I think most everybody's working their way in. Okay, so we sort of stopped there at the end about electron configuration and sort of how to write electron configuration, the order. Now, when we do write electron configuration in this class and pretty much every general chemistry class for the most part that you take, we do write the electron configuration in terms of filling, and that's what it's sometimes referred to as sort of the filling order. You will sometimes, if you sort of search around and look around, you'll sometimes see electron configuration written a little bit different than how we're going to do it. And that's based on energy. And what I mean by that is sometimes you'll see, as we were talking about at the end last time here, that the 4s orbital, for example, is lower in energy than the 3d orbital. So when we put it in, we go 4s and then 3d. You will sometimes see, as you search around, people write it kind of in order, like 3s, 3p, 3d. And that's actually based on energy and not filling order. And we'll talk a little bit about why that is as we go through this. But we do definitely follow the filling order. And that was that little sort of diagram that I made at the end there a couple of times that you can do. So again, remember, you can just make that little chart that we had, our 1s, 2s, 3s, 4s, 5s, 6s, 7s, and then start with our p's that start on the second energy level, 3p, 4p, 5p, 6p, 7p, and then our d's on the third, where they start, and our f's on the fourth. And remember, as we talked about, we always start up here and work our way this way and continue to zigzag back. Again, this in combination with, as we talked about earlier, 2 electrons max in our s's, 6 electrons max in our p orbitals, 10 for our d orbitals, and 14 there for our f orbitals. And that's going to allow you really to write any sort of electron configuration that you need by knowing those things. So we might as well start writing some electron configuration and sort of how that looks. So electron configuration basically gives you the order at which the electrons go into the atom. And we always, again, start with the lowest energy level and work our way up. And the lowest energy level, again, is at n equals 1 level. So, for example, we start with our first guy, which is hydrogen. Hydrogen on the periodic table is atomic number 1, which means it has 1 proton. And by default, what that means is it should also have 1 electron if it is neutral. And if it's neutral and it has 1 electron, we would again start up here at the top, and we would write the electron configuration as 1s1. 1s1, a couple of things here. This first number is the principal quantum number. That's that n number. This is the orbital or subshell that's involved. And the number on top is how many electrons. How many electrons are involved in that shell or orbital. So 1s1, and that's how you write it. The first one is a regular size 1. The s is a lowercase s, and the 1 is a superscript up on top, is how you do that. Now, 1s1 is electron configuration for hydrogen, and we can write or draw what is also sometimes referred to as the, let's put a box this way. I think I'll change color so we have some contrast here maybe. Go with green, why not? So we could also draw what is referred to as the orbital diagram. And the orbital diagram is basically either boxes or lines and arrows to represent the electrons. So for this case, we would have one box, which would represent the 1s orbital for hydrogen. And again, when that first electron goes in, it is going to go in the upwards direction. Now, to sort of tie this together with what we were talking about earlier, which is our quantum numbers, we could do our quantum numbers for this particular electron. And if we do it for this particular electron that's here, n would equal 1. Again, it's on the first energy level. And as we talked about before, L should equal 0 in that case. Again, L equals 0 to n minus 1. So 1 minus 1 is 0. Yeah, so I'll post this lecture up there, I think. Yep. So L will equal 0. And M sub L in this case would equal 0 as well, as there's only one orbital. And the M sub S would equal plus a half. So that would be the 4 quantum numbers for this particular electron. And again, the electron configuration would be 1s1. So 3 things here tied all together: electron configuration 1s1, orbital diagram, arrow boxes, and our 1s, and our quantum numbers here. Okay. So continuing on, let's take a look at helium, which comes next. Helium is 2 electrons, right? Atomic number 2. So again, starting at the top, this would be 1s2 in this case. If we did our orbital diagram for helium, we would have a box for the 1s. The first electron would go in upwards. And as we talked about earlier, the second electron would go in the opposite direction. I won't redo the 4 quantum numbers for this guy since it's above, but let's do the 4 quantum numbers for the second electron. The second electron, n would equal 1. Again, it's still on the first energy level. L would equal 0. Again, the 0 represents a s orbital, right? So that is what we're dealing with here. The M sub L is going to be 0, and the M sub S in this case is minus 1/2. Again, the electron is heading downward, right? And again, that is what we were talking about. This electron here, and now this electron here in the same orbital, they have 4 different quantum numbers. Again, the difference there, as we talked about, is really the spin quantum number. Continuing on, let's do lithium here. Let's try to find some room here on my screen. There we go. So let's go with lithium, which is 3. Again, lithium has 3 protons, which means it should have 3 electrons if it's neutral. Again, starting at the top, this is going to be 1s2. As we could see from our orbital diagram from helium, we have no more room in that orbital, which means we now need to zigzag back and head into our next orbital, which is the 2s. And in this case, we're going to do 2s1 in this particular case. Again, if we do our orbital diagram here, we would have a box for the 1s. Electron would go up, electron would go down. We would then have another box for our 2s. And again, that first electron would go in the upwards direction, like we've been talking about. Now we could also do the 4 quantum numbers. We could do the 4 quantum numbers for that electron, and why don't you do the 4 quantum numbers of that while I look at the question? And let's see. Yeah, so helium, right, is from the periodic table, right? Element, hydrogen. Yeah. And again, remember, as we talked about earlier, the atomic number, which is what you find on the periodic table, is the number of protons, which is the positive charge, right, basically. And if it's neutral, it's got to have an equal number of electrons. So kind of the same idea as what we were doing with atomic number, mass number, and those guys. So because we know it's neutral, if we know the atomic number from the periodic table, that should be also how many electrons you should have if it's neutral. All right, so let's take a look at the quantum numbers for this electron here. Again, the first 2 are the ones we previously did. They would come out the exact same. And in this case, will now be 2 because we're now on the 2nd energy level. L could have values now of 0 and 1 in this particular case. So there's an important distinction here when we look at these values. The value of L that is equal to 0 represents a s orbital, right? And the value of L that equals 1 represents the p orbitals. So when we're talking about a specific electron like we are in this particular case, the actual only L value that is appropriate here for that particular electron is 0. So this is the only one that is right for that particular electron, even though the p orbitals are available on that energy level. Because we're talking about this specific electron, it is not in the p orbital. It's actually only in the s orbitals. So the L value can only be 0 here. And that also means that the n sub L here would be 0, and the m sub s here would be plus a half. So again, this illustrates that although it's available, the p orbitals on that particular energy level, the actual electron we're referring to here is actually in the s orbital. So you want to be very specific, especially if you're actually talking about a specific electron like we are in this particular case. All right, then any questions on that there? Let's continue on then. After lithium on the periodic table there, the next element is beryllium, which has an atomic number of 4. And that means it has 4 protons and 4 electrons. So again, we're going to start at the very top there, and we'll have 1s2, 2s2. Again, here we are now going to fill up that 2nd s orbital. So our 1s orbital would have an electron up, an electron down. Our 2s orbital, electron up, and now an electron down in this particular case. And the first 3 electrons, if you did the quantum numbers, would come out exactly like what we had before. So let's do it for our 4th one here. The n is going to equal 2. The L, just like this guy over here, could have values of 0 or 1. But again, in this case, that second electron is also in the s orbital. So the value of L here would be 0 in this particular case. And that means that our M sub L would be 0. And our M sub S for this guy would be -1/2. Any questions on that part there? We could also see, obviously, that we have now filled up our s orbitals in our second energy level. So we would then have to now come back, if we have more electrons, and zigzag back to our 2p orbital. And that happens with our next element, which is boron, with number 5. So why don't you take a second, write the electron configuration for boron and the orbital diagram for boron, and then also do the 4 quantum numbers for the last electron that you put into boron and see what you come up with. So take a moment or two and do those 3 things: electron configuration, orbital diagram, and the 4 quantum numbers for the very last electron in boron, which would be the 5th electron. And let me look and see what we got. So I think this will answer both of your questions. Yes, the answer is when you get an L value that equals to 0, that L value of 0 represents an s orbital. So anytime you're dealing with an s orbital, the L value should be 0. Okay, so let's take a look and see. So we got 5. So again, we always want to start when you're doing electron configuration up here. So this is going to then be 1s2, 2s2, 2p1. Again, if you just count up the top numbers there, 2, 2, and 1, that is going to get you 5 total, which is the 5 electrons that we got there. So let's draw the orbital diagram in this case. We would need a box here for our 1s. We would need a box here for our 2s. And remember that the p subshell has not 1, not 2, but it actually does have 3 different p orbitals. That's the px, the py, and the pz. And that would represent our 2p subshell in this particular case. So as we kind of distribute our electrons, first one is going to go somewhere. Here we go. We're going to go up. We're going to go down. Next one will go up. Next one will go down. And that's our 4 electrons that we put in there. The next electron actually goes in the very first box, and it will go up, and so forth. So that's what the orbital diagram should look like. Now we want to do the 4 quantum numbers for our very last electron, which is this guy over here, right? So we want to do the 4 quantum numbers. I was going to write them over here. N in this case is going to equal 2, right? Because it's sitting here. And again, because n equals 2, L could have a value of 0 or 1. So hopefully in this case, which value should it actually be? Should it be the 0 or the 1? And because in this case it is sitting in a p orbital, the correct value is 1 in this case because of that. And so L does equal 1 because now the electron we're dealing with is not in the s orbital, but it's in the p orbital. And again, that is what the value of L equals 1 equals, is the p orbital. And let me just take a look here. You really should draw the other 3 boxes if you're asking for the p orbital, since we're only dealing with the 1 box there. You should draw the other 3 boxes, and I'll tell you why in just a second as to why it's kind of important to kind of draw it for a reference point, okay? So if our L equals 1 in this case, if you remember, our M sub L goes from values of minus L to 0 to plus L, which means technically this could be minus 1, 0, or plus 1 here. And the reason why you should draw all 3 of those boxes is because each one does represent a different M sub L. This is plus 1, this is 0, and this is the minus 1 box. So what we can see here by drawing all 3 of those is we have a reference point that our electron is actually sitting in, I wrote that backwards, and I'm sorry, I'm going to try that again. I'll get my minuses and positives. My bad. When you're right on top, minus 1, 0, plus 1. It goes in that order, just like that. I'm sorry. There we go. All right, so what we see now that I got the correct numbers there is the electron is actually sitting in the very first box, which would represent the minus 1 in this case. And we also see that the spin on that electron should be plus a half as it's going up. So when we start getting into sort of p orbitals, second energy level, get into d orbitals, f orbitals, you know, there's some choices as to where those specific electrons may reside. And you want to be very specific, especially if the question is a very specific question like this one, you know, what are the 4 quantum numbers for the 5th electron that you find in that particular atom. So the 4 quantum numbers, putting them all together sort of over here, are n equals 2. The L equals 1, which represents the p orbital. The M sub L represents minus 1, which means it's in the first orbital over here. And the M sub S is plus a half. Any questions on that there? Okay. So let us continue on. Might as well finish out the first few here on the periodic table. Let us go to the next element, which is number 6 on the periodic table. And that is, I always want to say carbon, but it is carbon. There you go. There. Let's say copper. It is 6, which is his atomic number. So we got 1s2, 2s2, 2p2. And again, if we do our orbital diagram, we're going to have 1 up, 1 down. We're going to have for our 2s, 1 up, 1 down. We're going to have our 3 boxes here for our 2p. We know the first one's going to go here, which is our 5th electron. Now you have some choices, and you have some choices, which is where you could put that 2nd electron. So you could put it here, and then perhaps you could pair it off. You can perhaps do this arrangement here, where we go 1 in each. And the correct answer is based off of a rule which is known as Hund Rule. And basically what it says is that the most stable sort of arrangement for an atom is one where we maximize parallel spin. So what does parallel spin sort of really mean? When we put 2 electrons in the same orbital heading in opposite directions, like we have in this example here, or we did in the 1s or the 2s, that arrangement is what is known as paired spins. Basically, the spins are paired opposite of each other, so essentially they kind of cancel each other out. So they're one going up, one going down. They sort of cancel each other off. If we do the arrangement like we have on the top right there, that is what is known as parallel spins. They're all heading in the same direction, right? And this is parallel spin over here. So what this rule basically says, which is Hund's rule, is we want to maximize that parallel spins. So when you have options for more than one electron in a subshell, they go in basically one at a time. So they'll go in one at a time, and then they'll come back and start pairing each other off. So that's an important sort of way that you know they go in there, because that's definitely going to affect the quantum numbers for that last electron. So let's talk about this last electron here. For the very last electron that went in there, the N value would equal 2. The L value would equal 1. Again, it's in the p orbital. And again, if you remember, the M sub L at this point could be -1, 0, or +1. And in this particular case, it is in the 0. So the M sub L here is 0. And also important, because of the way it goes in, we see that it's pointing upwards, which means that the spin of that guy is +1/2 in this particular case. Any questions on that there? All right, so let's continue on with nitrogen, which is 7. So continuing down our electron configuration, 1s2, 2s2, 2p3. And again, that's going to get us an orbital diagram. 1 up, 1 down for our 1s. 1 up, 1 down for our 2s. Again, we'll have our 3 boxes here for our 2p. 1 up, 1 up, and the third one is going to go up as well. And again, if we do our quantum numbers there for our last electron, N is going to equal 2. L still going to equal 1 because it's in a p orbital. Now our M sub L, we can see it's now in that last box, which has a +1 value. And we also see that the spin is upwards, which is +1/2. Any questions on where I got the numbers from or anything like that? Continuing on, if there's no questions, to number 8 there, which is oxygen. 1s2, 2s2, 2p4 in this case. Again, here we're going to have a box for our 1s, which would be filled in a paired situation. We would have a box for our 2s, also going to be paired. And now we have our 2p. First one going to go in here, second one here, third one here, and now the fourth one will come back to the first box and start to pair off the spin there. And that means that the last electron added here would have values of N is equal to 2. L is still equal to 1 because it's in a P subshell. And now the M sub L has now moved back to the -1 box. So M sub L is -1 in this case. And M sub S is -1/2 as it's pointing downwards. Any questions on that particular one there? We also could see from the orbital diagram that we got about room for 2 more electrons before we completely fill up the P subshell. So why don't we finish out those 2 electrons? So number 9 on the periodic table is fluorine. Means it has 9 electrons if it's neutral. And that means the electron configuration would be 1s2, 2s2, 2p5. Again, filling in our boxes here. 1 up, 1 down. 1 up, 1 down. up, up, and up, coming back, pairing, and now the next one will pair right there. And again, for that last electron, N would equal 2, L equals 1, because still in the p orbital. M sub L, we have now moved over back to the 0 for that guy. And our M sub S is going to be minus 1/2. And to finish out our first 10 here, which would be neon, which is number 10, it would be 1s2, 2s2, 2p6. And at this point, we would be filled up everywhere. 1s, 2s, and 1 up, 1 up, 1 up, coming back, and now we would pair them off in our 2p, and we'd be completely paired there. And at this point, we now would have an N equals 2 for that last electron. L is still going to equal 1. M sub L, we've now moved back to the plus 1 box. And our M sub S is minus 1/2. Any questions on how to write electron configuration? Orbital diagram are obviously identify the quantum numbers for each electron. As you can see, you can get very specific down to the electron as to giving the 4 quantum numbers. And again, it's important to know how they go into those orbitals, because, you know, if you just go like the 4th electron in oxygen, you may just think, well, maybe they go 2 at a time and it's sitting in the middle orbital rather than the guy at the end or the guy at the beginning. Any questions on any of that there? All right, so why don't you try then, why don't you write the electron configuration for, whoa. Why don't you do the electron configuration for calcium, which is number 20, in case you're not sure. So write the electron configuration, and then just electron configuration. You don't have to do the orbital diagram, but why don't you also figure out the 4 quantum numbers for, let's do the 12th electron. Why not? Let's just pick a random one. What is the 4 quantum numbers for the 12th electron in there as well? So take a couple of minutes here, write just electron configuration, and then try to figure out what the 4 quantum numbers are for that 12th electron. Okay, so let's take a look. So calcium is 20. So again, if you're looking at that little scale we made, again, you want to start at the top. So this is going to be 1s2, 2s2, 2p6. At this point, if you're not sure how many you put in there, you can just count the top numbers. So that's 6, 2, and 2 is 10. So we're halfway there. After 2p, then we go to 3s2. And then we go to 3p6. And now after 3p6, we actually go to, if you look at the little zigzag guy, we actually go to 4s next. And it would be 4s2 in this case. And that means that if you count up the top there, 2, 2, and 6 is 10, plus 2 is 12, plus 6 more is 18, and 2 more is 20. That would be the electron configuration for calcium. Any questions on the electron configuration part? So remember, if you can't remember the order, you want to just follow that kind of zigzag back and forth, and you'll get the right order. Now we had a second question here where we want to figure out the 4 quantum numbers for the 12th electron that went into calcium. So we can actually use the electron configuration to help us sort of figure that out. If we count the top number, that's 2, 4, 10. So the 12th electron is sitting inside the 3s orbital, right? And if we draw just the orbital diagram kind of for the 3s orbital part, we see that there's 2 electrons, which would imply that they go in this way, right? That would also imply that this first electron goes in upwards, which would be electron number 11, right? And the second electron that goes in goes downward, which in this case would then have to be electron number 12. And that's important for sort of our orientation. So what we do see is it's in a 3s orbital, which means that the n value here should be 3. That's what the first number represents. With an n value of 3, we can have an L value that runs from 0, 1, and 2 in this case. So we have 3 options. Only one of them is correct for this particular electron, and hopefully you chose the correct one, and that correct one is 0, because again, the 0 represents the s orbital, right? The p is represented by 1, and the d is represented by 2. So again, because we're talking specifically about that 12th electron, it's sitting in that s orbital, so the L value would have to be 0, which means if the L value is 0, the only value you could have for m sub L would also be 0, because remember, m sub L goes from minus L to 0 to plus L. So if L is 0, the only choice you have is 0. And also important to identifying the correct electron is we could see it is pointing downward, and that means that the m sub s here should be minus 1/2. Any questions on how we got to any of those numbers? Okay. So another sort of aspect, though, of it, if we look at this configuration and we look at perhaps a configuration that came a little bit before it. So if we look at, let's say, argon's configuration, which is 18. If we write argon's configuration, that is 1s2, 2s2, 2p6, 3s2, 3p6. And if we go back to calcium and we sort of put a box around that part of it, this part of calcium's electron configuration is the same as argon's. And there is another way that we could write the configuration for calcium that's very commonly done. Because that first part is the exact same configuration as argon, we could put a little bracket around argon. But remember, it's not 18, it is 20. So we would then just continue on with the electron configuration. And this is what is sometimes referred to as the noble gas configuration, which would imply that the guy that goes in here needs to be a noble gas. And if you're not sure, we're going to talk about it in just a second, but group 8 on the periodic table, the very last group is the noble gases. That's your helium, your neon, your argon, your krypton, and your xenon, and all those ons, basically. So this is another way that you could write electron configuration. So for example, if we looked at sodium, which is 11, and if we write out sodium's configuration, 1s2, 2s2, 2p6, 3s1, it would be sodium's configuration. If we go to the noble gas that comes right before sodium, that is neon, which we did at the very end last slide, which is 1s2, 2s2, 2p6, which is this part of the configuration. And we could, for sodium, write neon in brackets. Try that again, 3s1. Yeah? So we could do it this way as well. So you can write noble gas configuration, sort of a shorthand, if you will, for writing electron configuration. And it's always the noble gas that comes right before that element on the periodic table. So I'll try my best to hold this up. Maybe you can see it somehow, maybe. Or not. I just disappeared. Nice picture back there, by the way. There it is, maybe. So let's go that way here. So the noble gases that obviously come right before there as well. There we go. On group number 8. So the very last part of the periodic table, all the way to the right column. Whatever element comes after those, you go back to those guys. So why don't you try one just to make sure? Why don't you do why don't you do aluminum? That sounds good. Why don't you do aluminum, which is 13. So why don't you write the noble gas configuration, and why don't you do the regular electron configuration for it as well, just to make sure. Okay, so let's see. So we'll just start with the regular electron configuration. So that's going to give us 1s2, 2s2, 2p6, and 3s2, and aluminum will take us to 3p1 in this case. So that should be the electron configuration for aluminum. If we sort of cordon off up to here, that is 10 electrons. And again, that would be the noble gas that comes before aluminum. And again, that's neon. And then we would just continue on with our configuration here, which will get us to 3s2 and 3p1. Any questions on how to write electron configuration, noble gas configuration, quantum numbers, all that kind of stuff? So let's talk a little bit about what happens, though, if we do get something perhaps with a charge, right? So let's talk about that, I think. So if we do have something with a charge, we'll see some of those things. Let's say we had oxygen here with a -2 charge. So as we talked about when we were talking about atomic number, mass number, protons, electrons, and neutrons, it is the electrons that basically change when something gets a charge. So if you remember, we talked about that we have cations, which are positively charged, and those are from guys that lose electrons and become positively charged. We also have anions, which are negatively charged, and they are a result of the element gaining electrons. And remember that the positive charge means that it lost electrons, and the number is how many it lost from its neutral atom, while the negative charge means it gained electrons, and the number is how many it gained. So oxygen on the periodic table is 8, which means it has 8 protons and 8 electrons when it's neutral. And there we see a -2, which means it gained electrons, and it should gain 2 electrons, which means oxygen with a -2 charge should have 10 electrons in this case. And that's again where the -2 comes from. 8 positives from those protons and 10 negatives from the electrons gives us a -2 overall, which means its electron configuration would be 1s2, 2s2, 2p6, which would be 10 electrons. Now, if we had something with a positive charge, so let's just say, let's take our aluminum that we just did, and our aluminum with a +3 charge. So again here, the plus tells us it lost electrons. The 3 tells us it lost 3 electrons from where it started. And aluminum is number 13, which means it also hit 10 electrons. And that means that we would have an electron configuration as 1s2, 2s2, 2p6. That's interesting. They both hit the same electron configuration. By the way, both of those electron configurations of 10 is the same electron configuration as neon, right? So neon is 1s2, 2s2, 2p6. Now, all 3 of these guys, the oxygen with a -2 charge, the aluminum with a +3 charge, and the neon with no charge, they all have the identical electron configuration. Things that have the same electron configuration is what is known as being isoelectronic with each other. So things that have the same electron configuration are isoelectronic with each other. You may also notice, for example, if we took calcium that we did earlier, and calcium has a +2 charge. Calcium with no charge, like we did earlier, has 20 electrons. Calcium with a +2 charge, again, the plus means it lost electrons. The 2 is how many, would actually come down to 18 electrons, which would give it an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. And that is the same electron configuration as we saw earlier of argon on the periodic table. Argon and calcium with a +2 charge are also isoelectronic with each other. And there is a pattern in terms of ions and the periodic table. I'll draw my bad periodic table here. I kind of leaning. This is group 8 on the periodic table, and these are our noble gases. This is where we have our helium, our neon, our argon, our krypton, and so forth. So when we look at something like oxygen, which is right here, actually we'll go here. Oxygen is right here on the periodic table, and it gained electrons. And what it was able to do is go forward to the noble gas configuration. While if we look at, we did magnesium, I think. So magnesium is over here. And it lost 2 electrons, which allowed it to go backwards to that noble gas configuration and end up with the same electron configuration as that noble gas. And we even saw that with calcium, which is below it. Calcium backed up to argon in terms of its noble gas. And there's a significance to this because the noble gases, which are group 8, they are what are sometimes referred to as being chemically inert. They're extremely stable. And noble gases is essentially what everybody tries to achieve. So everybody tries to achieve the same electron configuration as a noble gas. That's really the basis of all bonding, both ionic bond and covalent bonding that we'll talk about. The whole basis of that is for everybody to end up pretty much with the same electron configuration as a noble gas, because that's an extremely stable situation. So how ions do it, cations and anions, for what is referred to as the representative members of the periodic table. The guys that gain electrons, they move forward on the periodic table to the noble gas that comes right after them. While guys that make cations, they actually move backwards to the noble gas that came right before them. So they will always end up in the same electron configuration as the noble gases when things lose and gain electrons. And that's specific for representative elements. So what do I mean by representative elements? Maybe we should talk about the periodic table here right now. Probably a good idea. In the middle are transition metals. They are a little bit different. And we'll talk about how they're different in just a second. But they're a little bit different, but everything outside the transition metal region will pretty much follow that path where they either go forward to the noble gas configuration or they'll go backwards to get to that noble gas configuration. Again, transition metals are a little bit different than that. Any questions on that part of it there? So this is sort of what we've talked about before. There's our Hund Rule that we want to maximize the unpaired electrons. So again, that's why when we put those electrons in, they went in one at a time in the upwards position and then went back and filled it in. But I think I'm going to steal some of this here to talk about the periodic table. All this is stuff we talked about already, arrows and stuff. Perfect. So I'm going to steal some of these things. So let's kind of officially talk about the periodic table here and some of the aspects of it. And actually, let me see. I think I might. Let me see if I can find one here. Hang on one sec. Let me just go forward. I think there's a periodic table here somewhere. There it is. And we'll go back. I guess that one. That'll work for now. Could actually talk about this. We'll talk about this and the periodic table here. We'll just use this periodic table. This will work. Perfect. All right. So first off, when we look at a periodic table, a group on the periodic table runs up and down. So up and down is a group. As you go left to right across the periodic table, that is a period. Now, when we talk about group numbers, and depending on the periodic table that you look at, there's many different sort of versions of numbering, but we usually use what is usually referred to as the representative numbering. And that on a lot of periodic tables is the A numbering. So you'll a lot of times see A's. You'll also sometimes see B's in there, and sometimes you'll just see numbers going 1 through 18. So we use this representative numbering, and right here is group number 1. This is group number 2 on the periodic table. We actually skip this entire middle section. And then group number 3 is over here. Group number 4 group number 5, group number 6, group number 7, and group number 8. So although it is technically 1A, 2A, 3A, 4A, most people don't use the A. Most people just call it group 1, group 2, group 3, group 4, group 5, group 6, and group 7. Now, when we look at group 1, for example, and on most periodic tables, this box right here is hydrogen. Hydrogen is not part of group 1, even though it's sitting over there. Hydrogen is just over there for a particular reason, but group 1 actually starts with lithium, which is right here in this particular box. And lithium, then underneath it, we have sodium. We got our potassium, our rubidium, all those good things. So that is really where group 1 starts, is with lithium. Over here in group 2, we have our beryllium, just to kind of give you some reference points. Over here, this is boron. We have carbon, nitrogen, oxygen, fluorine, and neon, to kind of fill it in, if you will. And aluminum, silicone, phosphorus, sulfur, chlorine, and our argon here. And over here is our sodium and our magnesium. And that's our calcium. Okay, so we got sort of a periodic table filled in. So group 1, again, starts with lithium, not hydrogen, and then as we go across the other ways. Now, the periodic table is broken into several sections. There's usually right around here-ish, kind of coming through here, is kind of a staircase, and a lot of periodic tables is sort of delineated. And everything to the left of that staircase are what are known as metals. And metals are good conductors of heat and electricity. They are usually shiny, right? In addition, metals are all through here and all the way to the left. Above the staircase to the right, so where the staircase kind of comes through, above it to the right, these are all nonmetals. And nonmetals are pretty much the opposite. They're dull, brittle. They're bad conductors of heat and electricity. Now, the reason why when we talk about over here on this side that hydrogen is not part of group number 1 is, and this is usually where we're in class, and I point to the really nicely looking periodic table on the wall, but we'll pretend here. Let's go with, we'll go with red. Hydrogen over here, which on most periodic tables can be found here. Older periodic tables, they would actually put it over here as well in both places. But hydrogen is actually a nonmetal. So even though it's hanging out over there on the left-hand side of the periodic table with all of our metals, it is actually a nonmetal. So that's why it's really not part of group number 1, which actually does start with lithium, because it's actually a nonmetal. Hydrogen has a lot of kind of unique characteristics, which is why it's over there in group 1. Sometimes we almost treat it like a metal, a positive sort of guy, but it's technically a nonmetal. And again, like I said, older periodic tables, you'd actually find it on both sides. You sometimes see it listed both ways. But the other part of the periodic table is where that staircase is, as it's coming down in this region. And where that staircase is, that is what are known as nonmetals. Not nonmetals, sorry. That is what is known as semimetals, or metalloids. So semimetals or metalloids are those guys that come down like silicone, arsenic. So somewhere in this region here, you know, they kind of come down as like twos. kind of coming down this staircase, you know, as it comes down this way. And semimetals are metalloids. They're elements that have characteristics that fall both as a metal and a non-metal. So certain characteristics of those guys are very much like what you would find with metals, but the same element will also have characteristics that are very similar to non-metals as well. So a lot of them are conductors or semiconductors in that sort of area. And again, because they have sort of properties of both sides. Now, when we look at the periodic table as well, right here in the center between group number 2 and group number 3, these are our transition metals. And our transition metals, one key aspect of our transition metals are that they have pretty much the ability to make multiple types of positive charge. So they have a variable type of charge, which is a common thing that transition metals have. Other metals have sort of fixed charges when they do make charges as well. So in addition, on the two bottom guys down here, these two rows here, if you follow the numbering on the periodic table, this is 56. This is like 57. And then if you go next door to it, it goes to 72. So the numbering really doesn't match here. And that's because this first row that we see at the bottom should technically be, this is like 58, 59, and so forth. This row technically should fall right in here. And that's why this is what is sometimes referred to as the lanthanides, because that's the element it follows. Same thing if you go right below it, if you follow the numbering, this is like 89. This guy over here is like 104. And that's because this second row down here is technically where 90, 91 is and everything like that. And this second row technically would go right in here. And that is what's known as the actinides because they follows that element as well. So the lanthanides and the actinides would go in there. And because that technically would go in the transition metal region, they are sometimes referred to as the inner transition metals. Because technically that's where they go. I've only one time in my whole life seen a periodic table where they did that. And it took up a whole entire wall because it would spread out your periodic table like really wide to put those guys in. So they usually are found on the bottom, but atomic number wise and technically speaking, they actually do follow those two elements that we would see there as well as the inner transition metals. Now, a couple of things about metals and non-metals in terms of just some properties. Metals are typically solids at room temperature. There's only one metal that's not a solid, and that is mercury, which is number 80. And that would be, so that's 72, right? Yep. 73, 74, 75, 76, 77, 78, 79, 80. And somewhere in this area here, it'd be mercury. So mercury is the only one that's not a solid at room temperature, and it is a liquid at room temperature. And all the non-metals, though, they do come in a variety of sort of characteristics. Some are metals, some are gases, some are solids, some are liquids. So they come in a much wide variety of sort of states. Now, lastly, just to kind of finish up our little conversation here about the periodic table, as I butchered this whole picture here with writing all over it. Let me see. When we do look at the periodic table, there are groups that have certain names. And the first one that has a certain name is group number 1. So group 1 is the alkali metals. Right next door, and again, the alkali metal starts with lithium. Right next door is what are known as the alkaline earth metals. Alkali and alkaline, it really means basic. So that's where we find a lot of bases come from. So things like sodium hydroxide, potassium hydroxide, calcium hydroxide, magnesium hydroxide. Those are where a lot of bases come from. If we come over to group number 7 here, I'll just write it here, but it starts with fluorine, our chlorine, and so forth. These are our halogens. So group number 7 on the periodic table is our halogens. And as we talked about last time here, group number 8 is our noble gases. So as I talked about before, noble gases are chemically inert. They don't react with a lot of things. They react with themselves, but not others. But they're not very, very reactive at all. Halogens are a lot of our diatomic guys. So remember, like our fluorine is F2, Cl2, Br2, I2. A lot of those diatomic guys come down through here. So this is the general sort of setup for a periodic table. You do need to know the parts. You need to know where the metals are, the nonmetals are, the metalloids, transition metals. You need to know which way groups go. 1, 2, 3, 4, 5, 6, 7, and 8. Periods, by the way, as you can see here, go again left to right. So this would be period 2 going across. Going this way would be period 3, period 4 heading that way across. You also need to know the names of those groups. Like group 1 is the alkali metals that starts with lithium. Group 2 is the alkaline earth metals. Group 7 is the halogens, and group 8 is the noble gases. Any questions sort of on the periodic table? All right, I think so the question is, let's see, why is there? It's a very good question. On periodic tables, and depending on sort of when the periodic table was made and when it was printed, this last sort of period down here is where they oftentimes will put, I'll just kind of scribble on it. So this last little bit over here is where they oftentimes will put elements that they're still deciding whether or not they're going to be elements. So sort of like man-made elements, if you will, where they're going to be in terms of names and stuff like that. On some periodic tables, there's not even boxes there. So for example, again, I don't think if you can see my periodic table, but that angle maybe. If not, you get a nice picture that you can see. There it is. So let's go that way. So you can see that there's like nothing over there in that region on my periodic table, and my periodic table is printed way early. So the pen is printed. You know, there may be something there. There may not be something there. You may even see some really weird symbols that are there. And that's sort of why in this particular one, that probably at the time when they made it, there's really nothing like occupies sort of that spot. And that's probably why it's empty. Other questions on that there? Okay. So I think at this point, that's enough torture for today, right? I think so. I think we're going to stop here. We're almost pretty much done with chapter 2. We just have to talk about a little bit more about electron configuration. I started talking about things with charges and then I stopped. So we'll talk about what happens with things with charges. We'll also talk about on Monday electron configuration for our transition metals is a little bit different. Things happen there as well. And we'll finish up talking about the periodic trends. And that will be good on Monday because after lecture, then you should be good to do experiment 3, which covers all that kind of stuff. So again, a reminder that we'll do experiment 3 on Monday after we lecture, and that we should definitely now be able to get through all that material. And then you should be good for chapter experiment 3 on Monday. Any questions on any of that stuff? Now, again, so no lab today. You don't have to worry about any physical lab to turn in or do any lab. Again, we're going to move it to Monday. Just to let you know, I think maybe sometime soon, maybe even over the weekend or sometime at the beginning of next week, we're going to have some type of, I'll call it a quiz. It's not really going to be a quiz that counts really for anything. But it's going to be a, sort of like a quiz. Maybe it'll be on some lab safety or something like that. just to give you some questions to answer. But mainly what it's going to be for is, again, we're coming up in, I think, about a week from Monday is our first exam. And a reminder that part of the requirements of this class is obviously you need a computer and laptop with a camera and microphone so that you can be proctored while you're taking an exam and stuff like that. So again, we're going to probably use the proctoral proctoring program. So you don't have to worry about sort of the first exam and figuring all that stuff out. I'm going to put sort of a quiz up, and that will allow you to log in, and you'll get a sort of understanding of how that whole thing works. And that way you can kind of get yourself set up the way you need to, and you don't have to worry about sort of the proctoring aspect of it and the exam. So again, that should be coming up. I don't know exactly when, and maybe it will be open this weekend or something like that, or definitely towards the first part of next week. So officially, it's not going to really count for any sort of overall grade or anything like that. It's just going to be sort of a way to allow you to sort of understand how the whole computer proctoring sort of thing is going to work, as you may not be obviously familiar with it or all aspects of it and stuff like that. Yeah, so you'll be allowed to use paper and stuff like that in the exam. In fact, there will be some questions on the real exam, maybe not even maybe the practice one, but you'll be able to use paper and stuff like that to work out problems, and obviously upload your work is going to be part of what you'll have to do for exams, and it should be okay. But again, I just want to kind of get that, maybe give you an assignment or something to do using that proctoring program. So again, you can sort of understand how it works and stuff like that. And again, it does require that your camera and microphone be on and working. I would say probably maybe for exam. I think it should be okay. I think I'm trying to think here. I think maybe for exams or quizzes, maybe try to use paper if you could, and a pen or a pencil would be better, I think, just to be good on that sense. Yeah. Other questions or anything like that? Okay, so just be watching for that. Yeah, so in terms of periodic table, so let's just talk a little bit about the exam in terms of what you'll be given and sort of what you'll see. So as of now, the exam will most likely be taken on Canvas, okay? So you'll log on to Canvas, actually take the exam through Canvas. And when you open the exam, the regular exam, maybe not this practice one that we're going to do, next coming up, but the regular exam, when you open up, you will be given a periodic table that you could use, and it'll be actually built into the exam so you can see it. And you will also be given any type of conversions that you may need, like maybe, there's 12 inches in a foot, 453 grams in a pound, something like that. A reminder, though, that you will not be given any type of formulas like, D equals M over V or E equals H times the frequency or any of those type of things will not be provided for you. But any type of constant values, we had a constant there, like the speed of light, for example, that would be provided for you. Planck's constant would be provided for you, and those type of numbers will be provided, but no formulas. So the C equals the wavelength times the frequency you need to know. Periodic table would be provided for you and stuff like that. So you'll log into Canvas, you'll take it through that. That stuff will be built into there. You should use, obviously, what is provided for you. If on Canvas or something like that, I think that maybe you might have an issue with seeing a picture or anything like that that I didn't put in there. I also will include a PDF file that you could click and open and actually see it as well. So that will allow you to kind of see it and that type of stuff. Yeah, so I think if we use the proctorial, yeah, so when we'll use proctorial, and you will just do it through there. You don't have to log into the Zoom as well. So you don't have to log into the Zoom either. So we're going to give a try here again, just sort of make sure everybody's on the same page, hopefully work out any sort of kinks that there might be with it. And, before we get to kind of the real exam. Okay, does that sound good? So at least we'll kind of give that a try and stuff like that. So it won't be probably the next day or two, but, probably towards the end of the weekend, again, the beginning of next week, we'll have something like that. And like I said, I don't know if it will really count for anything for true, and you don't have to really worry about the materials. It's really just more so for you to sort of get a feeling as to, you know, what you're allowed maybe to do, what it won't allow you to do, obviously, while you're taking the exam and stuff like that. Any questions on any of that? You can, it's okay if it's okay if there's some background noise. I believe, if I'm not mistaken, there's sort of different levels I could kind of set it to and stuff like that in terms of, you know, security. But if you can, probably during the exam, and that's other things you might want to try to maybe work out before you take the real exam. If you can, maybe try to get into an area where, if you can do that, you know, it's maybe not too loud or too many people around and stuff like that. So, you know, those are things as we go into the exam and using this, you just want to kind of think about, you know, an area maybe if it's possible for you to move. If you use something like a laptop or something, try to find maybe a quieter area and stuff like that, so it doesn't pick up all that kind of stuff. But you probably will need to have your microphones on as well, and the video part as well. Again, okay. Other questions? Okay. And I think you'll be okay if it's just a little bit of background noise. I don't think it's going to be that big of an issue or anything like that, as long as you don't have somebody standing next to you yelling at you, right? And the idea behind that is so you don't have anybody yelling at you the answers, I suppose, right? And all that kind of stuff. That's okay. Just try to do your best. If if it's an issue or anything like that, I think I have the ability to look at what was going on, and you know, I think it should hopefully be okay. Okay. So I guess it would be still the same disturbance that you would hear as well if you were just sitting there without the microphone on. You would still hear it. Nobody else will be able to hear it because it would just be you, obviously, and stuff like that. And I understand I got construction going on as well next door, so it's very loud as I'm trying to lecture. So hopefully you can't hear too much of that either, as well. All right. Any other questions on any of that? So just keep that in mind. Like I said, experiment number 3, we're going to move to Monday. We'll finish up chapter 2 on Monday. Hopefully we'll roll into also the next chapter as well. And other than that, like I said before, the lectures will be up online. This one will be up there as well, and today's lecture before it. Like I said, it does take a little bit of time to kind of get it up there, but you could find the links to those up in our module section. And like I said, unfortunately, the first one didn't work very well. Something weird happened. Yeah, so that's my understanding as well. In terms of before you go to take the exam, the quiz, or anything of that sort of nature, make sure that you maybe use the restroom first. You don't leave the camera view or anything like that. You shouldn't really walk off of the camera or anything like that. That's definitely going to flag you, yeah, in terms of something not good. And in general, you shouldn't leave really the viewing area. Kind of like if you're taking the exam in person, you typically want to get up, walk around, leave the room, and all that kind of stuff. So try to get yourself all set and good to go for the length of the exam, you know, before you start, because you really shouldn't leave, because obviously don't know what you're doing if you leave and that type of stuff. So sort of keep that in mind. Okay. So try to definitely for the real exam and all that kind of stuff, try not to vary or move or anything like that in sense of walking away from obviously being the camera part of it and stuff like that. Otherwise, they will definitely probably flag you, I'm pretty sure. Okay. And then I won't really know what happened if you walked away. Yeah, so no homework or anything like that. That's for today. No lab or anything for today. The homework, just so you know, again, is posted on the Canvas site under Exam 1. So if you want to get started on that, you probably could do a majority of it for Chapter 1. You should be able to do. And then obviously for Chapter 2, you could probably do a majority of that as well if you want to get started on that. Again, a reminder that the homework will be due on exam day. So the day we take the exam, there will be an assignment like how you're uploading your labs. There'll be an assignment up there that you can upload your textbook work up on those days. So again, I think exam 1 is chapters 1, 2, and a little bit of 3, I think, as well. You'll be able to upload chapters 1 and 2 and a little bit of 3 on the day of the exam. Other questions or anything like that? Okay, so think that's good for today. Whoa. Hang on one sec. Let's see. Okay. I'm not sure. I would have to look at it. I'm not sure if I know exactly what you're asking there, but hopefully you did the calculations like we talked about. So I hope that's what you got. Um, yeah. So, all right. I'll take a look at it at that point. Other than that, have a good weekend. Yes, 1 week down, 7 to go. Never too early to start counting, I always say, right? Yeah, so the exam will take place during our time. Yeah, so it's going to be synchronous. So you do need to take the exam during this scheduled time. So we'll probably take the exam starting around lab time. It'll probably be open because we have like a 3-hour window or so, right? So it'll be take on that. We may even start it around lecture time or in the middle of lecture, kind of maybe lecture for just a little bit, and then you could go off and take the exam. But again, everything in this course does need to be done during the time period that's scheduled. So the exams will take place during that time period. So my guess is it'll either start towards the end of lecture and you could roll into lab and give you that kind of good window of time, or it'll start at probably around the beginning of when lab would start, would be when we would take it. Other questions? Okay, so if you're good, then now have a good weekend. If you didn't type here, make sure you do that in the chat box, and I will see you on Monday. Thank you, you guys too. Have a good weekend, everybody.